Hi. In the earlier video, we explored the idea of the reflection of sound, and we also saw the audible range of sound, right? The human audible range, which is 20 hertz to audible frequency range of sound, which is 20 hertz to 20,000 hertz. And we also saw how we can make good use of these two properties, which is primarily your reflection of sound and to maximize the effect of the sound, right? Like placing, making sure that everybody in the auditorium is able to hear, or people who are not able to hear, how can we help them primarily through a hearing aid, right? So all this were we're exploiting the properties of the sound, which was reflection and frequency. Now, in this section, we will also talk about how we can extend this for high frequency wave sound waves, how that can be of help. So typically, sound waves which are greater than 20,000 hertz have even better use than the normal sound, and they have a wide range of use, and we'll take a couple of examples here, and we'll touch upon the other aspects as well. As we know, the ultrasound waves are waves with very high frequency, which you cannot hear, and they are waves that are greater than 20,000 hertz or 20 kilohertz. And the classic application of that is by a device called sonar. So sonar stands for sound navigation and ranging. So these devices are primarily used by ships, primarily to determine the depth of the ocean. So a ship that is in ocean, let's say the ship that is sailing in a deep ocean, typically typically uses this device called sonar to be able to know this depth, the depth of that ocean at that point in time. So it all uses the properties of sound, which is reflection of sound primarily, and which means that your sonar has two components. One is your transmitter, so, and the second part is your detector. So these are the two components of that sonar device, and the job of the transmitter is to emit sound waves, and that sound wave will, once it hits the bottom, it will come back, and that will be caught by the detector. And we know the speed of the sound in water. We can experimentally find the speed of sound in water, and with that we will be able to find out, calculate the distance that it traveled with the speed of the sound and the time it took for the detector to receive back the sound. One should be able to calculate the distance, right? And once you divide that by half, it will be the depth of that ocean, right? So this is a common use case. This is a common usage of ultrasound. Typically, bats, right? Bats also typically use emit ultrasound waves to primarily spot their prey. So typically, bats emit ultrasound waves just like your sonar device. The ultrasound waves so think about this as a bat, and this is an insect. So the bat would emit an ultrasound wave, and based on the reflection that it hears back, it will be able to detect that sound back, and then it will exactly be able to pinpoint where that insect is. So bats use that. And there is a variety of wide range of use of ultrasound waves coupled with this property of reflection. Sometimes you must have heard of ultrasound scans in hospitals, and those are the primary use of that is to scan your internal body parts, internal organs, primarily by emitting ultrasound waves, and based on the reflection of the ultrasound waves is how the presence of any additional growth of that organs or the functioning of that organs are all scanned. Right? Say if you have a huge material, how would you know if there are any cracks inside the material? If there is a huge iron object, and we know that if there are cracks outside, but how would we know that if there are cracks inside that huge iron bar or that block, right? Again, ultrasound waves would definitely help, and the way you would employ that is think about a huge iron block, and you emit ultrasound waves from one side, and let's say you have reflectors on the other side, and based on which you should be able to if there are no cracks, it should hit the reflectors and it should come back to your to the original spot. But rather, if you are able to if you are able to you have detectors on the other side. I shouldn't say reflectors. These are detectors on the other side. So the ultrasound waves that you emit from one side, if there are no cracks, it would be successfully detected on the other end. But rather, if there are some cracks in between, the waves that you emit from one side will not be detected on the other side, right? And those would most likely be reflected back to your origin, or it will be lost. So in those scenarios, you can find out that there is some problem internal to that particular object. So this is another important use of ultrasound waves, wherein to identify any internal cracks or internal damages in a huge object, right? So ultrasound waves are also used in deep cleaning. Typically, when in a very small tube or a small corner where it's very hard for a brush or anything to go and clean. What they typically do is they fill some chemicals into that small hole, and then they emit a high frequency ultrasound wave on that corner, and that vibration would clear off all the dirt from that corner, and it will come out. So that's another use of ultrasound waves. So primarily it is in sonar, ultrasound scans to detect organ abnormalities, detect breakages in materials, cleaning, deep cleaning small corners and all that. Even in medicine, ultrasound waves are used to break kidney stones and all that. So something if again high frequency ultrasound waves when directed to a kidney stone, that vibration can go ahead and break that kidney stone, and that will get diluted. That will break off, and that will eventually come out of your urine. Right. So those are some of the uses. So just to come back to this example of how to detect breaks, you have ultrasound waves coming. Emitted. You emit from one side of the huge block, and you have detectors on the other side. And if there are no breakages, then all the waves that you emit from one side will be caught by the other end. Whereas if there is a break, you will not hear back. These detectors will not be able to detect the waves that you send from this end, and this can help you explain that that there is not everything is okay inside this object. So the last step that we will talk about is the functioning of the human ear, how we respond, how we perceive sound. So far, we have taken all these detectors and all. Human ear is able to detect the sound, and how exactly the human ear senses and detects that sound is what something that we'll spend time on. And I have already captured some notes about the behavior of the human ear here. So this is a bit of theory which we'll have to understand. And typically the human ear has three parts. The external part that is visible outside is the outer ear, and then there are parts which make up the middle ear, and there are parts that make up the inner ear. Right? So it is through these three parts that sound is being perceived by the human ear. Right? So in a sense, the job of the human ear is to do five things. First is to receive the sound, right? So as the sound propagates and reaches the ear, it has to receive it. So which means that it has to direct all the sound and channelize that sound, right? And that's the whole role of the outer ear, which is called pinna, and that is to receive the sound that is propagated till the ear. The second part is to direct that sound. All the sound needs to be directed and channelized, and that's the role of the auditory canal. So this is your auditory canal, and the job of this is to channelize the sound that is received, right? So the outermost part is to receive, then it is to direct that sound. The third part is to sense that sound, right? So we know that, how do you sense a sound? Is by, we say the sound propagates by vibration, right? The sound propagates by the vibrating object vibrates the nearby air particles. The vibrating air particles vibrates the nearby air particles, and that's how sound wave propagates. So this sensory layer, as part of the outer ear, has the eardrum, which vibrates upon the arrival of the sound, right? So although the vibrating air particle comes in and hits the eardrum, and which vibrates, right? So that becomes, which means that it has perceived, it has sensed something, it has sensed the sound wave. Once the eardrum vibrates, it means it has sensed that sound wave. Then comes the middle part of the ear, and the job of the middle layer is to amplify the already sensed sound. So if the eardrum has already sensed that sound wave, the job of the middle ear, which has three bones primarily, anvil, hammer, and stirrup. So the job of these three bones are to amplify that sound, just like how in the hearing aid, we were able to amplify that electric signal. So the job of the middle ear is to amplify the sound waves that have come in. Now, once that sound wave is amplified, then comes the role of the inner ear, and it starts with cochlea. So the component of cochlea's job is to, the amplified sound waves, right? The amplified sound waves by the middle ear is now converted into electric signals, and it will be sent to the brain. And it is the brain that ultimately perceives that sound wave, right? So the role of the cochlea is to convert the amplified sound wave by the middle ear into an electric signal and pass it on to the brain. And it passes on to the brain through the auditory nerve, and that reaches the brain for it to respond to. Right. So this is the whole working of the human ear. And with this, we come to the end of this chapter on sound. And in the next video, we shall go over the in-text questions, and we'll then go over the exercises as well. Thank you.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.